Hello and welcome to this second example of finding second order system responses in control systems. In the previous example, we derived the result for a critically damped response of our RLC circuit with the use of Laplace transforms. In this section, we're going to look at an alternative, maybe simpler method to do the same thing. But we're also going to use this method to examine overdamped and underdamped cases as well. So in the last example, we derived the result for ourselves using the inverse Laplace transform. And whilst it's important that we learn to do this for ourselves, it shouldn't come as a surprise that these results have already been derived before, not just necessarily for the critically damped case, but for the underdamped and overdamped cases as well. So to examine our alternative method that we're going to talk about more in this video, we have to return to the transfer function that we defined for our RLC circuit. And we're going to use the same circuit here as the previous example where the output of the circuit is the voltage measured across the capacitor. And we previously derived this equation for the transfer function as well. G of S in the S domain is equal to 1 over SRC plus S squared LC plus 1. Now this alternative method, or this shortcut, involves us determining the roots of this equation. And the form that these roots take tells us something about the form that the resulting equation in the time domain is going to take. So really what we're doing is we're sort of leapfrogging over the Laplace transform. Hopefully we won't have to do any Laplace transforms in this video. We're going to sort of jump that by using this root finding method, and we'll see that in practice in this example and the next examples as well. Okay, so when we find the roots of our characteristic equation here, we're going to use this formula. It's S equals minus R over 2L plus or minus the square root of R over 2L all squared minus 1 over LC, still under the square root there. And this is kind of an adaptation of the quadratic formula that's used to find the roots of a quadratic equation. It's a similar idea, but you'll see here that we've got things in terms of R, L and C components instead. We're going to look at three possible scenarios that are going to result as finding the roots of this equation. And we'll see some examples in just a moment, but there's the three possible scenarios that we can encounter depending on whether our circuit is critically damped, underdamped, or overdamped. And just as a reminder, we've talked about this in a previous video, but here's the conditions for these damping scenarios. If a circuit's overdamped, then the value of R squared will be greater than the value of 4L over C for those component values in the RLC circuit. If the circuit's critically damped, R squared must be equal to 4L over C. And if the circuit is underdamped, the value of R squared must be less than 4L over C. Now, whether the circuit is critically over or underdamped is going to affect the value of the discriminant of our equation here. And by the discriminant, I'm referring to the bit that's under the square root. That's the discriminant of this circuit here. So let's look at critically damping first. If a circuit's critically damped, the value of the discriminant R over 2L squared minus 1 over LC, that's the bit that's under the square root there, that's our discriminant. If the circuit's critically damped, the value of the discriminant will be 0. If this is the case, the result's going to take this form here. Vc of t, so notice we're in the time domain, we've skipped straight over Laplace transforms. Vc of t is equal to Vs plus A1 plus A2t, close brackets, e to the power minus at. Now in this case, the value of a, little a, in the power of the exponential there is r over 2l. A equals r over 2l. But these constants a1 and a2 are unknown. We need to work those out. If the circuit is underdamped, the value of the discriminant, and again the discriminant doesn't include the square root itself, it's just the bit that's under the square root, r over 2l squared minus 1 over LC. If the circuit's underdamped, that discriminant is going to be less than 0. If this is the case, the result is going to take this form. Vc of t, so that's our output voltage again in the time domain, the voltage across the capacitor, is equal to Vs plus, in brackets, A1 cos omega t plus A2 sin omega t, and that's all multiplied by e to the minus at. And again, A is r over 2l. We're given that A is r over 2l. Omega, in this case, is 1 over root LC. But again, these constants A1 and A2, we're going to have to work those out for ourselves. The last case is if it's overdamped, if the circuit is overdamped, the value of the discriminant is going to be greater than 0. And if this is the case, the result's going to take this form. Vc of t equals Vs plus A1 e to the power S1t plus A2 e to the power S2t. Again, the values of A1 and A2 are constants that we're going to have to find the values of. The values of S1 and S2 are actually the roots of the equation that we would find by using the whole, not just the discriminant, but the whole of that equation for the roots that we saw previously. Now, in this video, we're just going to look at one example. We're going to look at a critically damped example. But in our next videos, we're going to look at underdamped and overdamped examples as well. So over the course of the next 3 videos, we'll have seen an example of each. So for our critically damped example, we're actually going to use exactly the same circuit that we used in the previous example. And in the previous example, we derived the results using Laplace transforms. So this is actually quite a good test because we should hopefully get exactly the same results using our new root finding method. But if you recall from our last example, we had an RLC circuit like this, where the output is the voltage measured across the capacitor, and the component values that we used were R equals 120 ohms, L equals 36 millihenries, and C equals 10 microfarads. Let's also keep the input the same as the example that we used previously. Let's say it's a step input of 5 volts that occurs at time 0 seconds. So we're keeping everything consistent to the previous video where we did this exact same thing with Laplace transforms. Let's hopefully get the same result. Okay, so we already know from our previous example as well that these components meet the requirements for critical damping. We talked about this in our previous video, but let's go ahead with our root finding method to hopefully get something comparable. But let's first go ahead and calculate the discriminant in this case. And remember those 3 cases above. Because we're critically damped, the value of the discriminant should be equal to 0 for a critically damped case. So let's see if that's the case. The discriminant here is R over 2L all squared minus 1 over LC. Well, R in this case is 120. L is 36 times 10 to the minus 3. And C is 10 times 10 to the minus 6. And so when we substitute all of those in place, we get something that looks like this. Which we can sort of simplify down a little bit. 2 times 36 is 72. 36 times 10 to the minus 3 times 10 times 10 to the minus 6. Well, the 36 and the 10 multiplied to 360. The 10 to the minus 3 and the 10 to the minus 6 multiplied to 10 to the minus 9. So we have now 1 over 360 times 10 to the minus 9. We can go on simplifying and whatnot, but if we just put all that into a calculator, short answer is it comes out at 0. So we've met this requirement for critical damping. And again, going back to those 3 cases, because that's the case, we know that our result is going to take this form here. Vc of t is equal to Vs plus A1 plus A2t, all multiplied by e to the minus at. So notice again, we've not mentioned anything in the S domain, no Laplace transforms, anything like that. We've got our output expression here already in the time domain. The only thing that remains is to find the values of these unknown constants here, A1 and A2. Okay, so to do that, let's first return to our full equation for the roots of the function. We only looked at the discriminant there, the bit under the root, but the whole equation looked something like this. Remember not to waste your time. We've already calculated the value of this discriminant as 0. So straight away, the square root of 0 is 0. We can get rid of that. We're just left here with minus r over 2l. And putting our values in, we have something that looks like this. And that simplifies to this, 120 over 72 times 10 to the minus 3. And that comes down to minus 5,000 over 3 in a sort of fractional form, rational number there. Try to avoid decimals wherever possible. In some examples, it's not really avoidable, but if we can avoid doing so and your scientific calculator gives you an answer as a fraction, it's best to preserve that accuracy rather than starting to round things. Now, in truth, this has also been a little bit of a waste of time because we have already defined the value of a in our function. We don't know what this value of little a is yet, but in the initial 3 cases, we said that a is defined as r over 2l. Well, notice that in this critically damped case, that because that discriminant is 0, this root disappears, we're actually calculating or reduce this calculation down to just minus r over 2l. So really what we're working out is actually minus a. So we could have just used the definition of a equals r over 2l. But here we've kind of done it the long way, the sort of proper way, as it were. We've seen where that comes from. But either way, we've got now the value of minus r over 2l is minus 5,000 over 3. So that means that r over 2l, in other words, a, is going to be plus 5,000 over 3. Okay, so let's populate our result with what we know so far. We were given this sort of blank or sort of exemplar case response here. VC of t equals Vs plus A1 plus A2t, all multiplied by e to the power minus at. And that was for the critically damped case. Now we know that a is 5,000 over 3. And so we're going to substitute that in. Just be careful here, because yes, a we worked out to be plus 5,000 over 3, or a positive number, but it's still going to be negative in this formula, because notice that the formula is minus at. So we have minus 5,000 over 3t as the power of that exponential term there. So just watch out for that. If it worked out to be negative, then it would be positive. But in this case, we're going to get a negative power there. We now know the value of a, little a, but we don't know the values of capital A1 and A2. So to do this, we must consider the initial conditions of the circuit in order to help us solve the equation. In our case, we're going to make the assumption, like in all of our examples, that the initial conditions are 0. In other words, when time equals 0, the output voltage is 0, which makes sense, providing that the capacitor is not already holding some charge, or there's not already current flowing in the circuit. We're assuming that our initial conditions are 0. And so if this is the case, let's take that same formula again that we have so far. Notice as well that we now know the supply voltage is 5 volts. Vs is 5, because we're applying that same 5 volt step input, and because it occurs at time 0, it's just a constant. We have that 5 volts as our Vs term there. We have this equation here, and what we're going to do is, assuming those initial conditions, that Vc is 0 when t equals 0, we're going to go through here every t is now 0 and vc is now 0 on the left hand side. So we have something that looks like this. A2 minus 0 here, A2t is now A2 times 0 because t is 0. That term is going to disappear. And 5,000 over 3 minus 5,000 over 3 times 0, which is 0. So we have something that looks like this. 0 equals 5 plus A1 times e to the power 0. Be careful here, e to the 0 is not 0. Anything to the power 0 is 1. And so A1 times 1 is just 1. We have 0 equals 5 plus A1, and that means that A1 must equal minus 5. Okay, so we found A1. To find A2, we have to differentiate the expression and then set these initial conditions to 0 also. So let's write out that differential first in terms of d dt. We've got d vc by dt on the left-hand side, so we're differentiating that output vc with respect to time. On the right-hand side, we've got d by dt, all of the rest of this, 5 plus a1 plus a2t, all multiplied by e to the minus at. We're going to differentiate all of those terms, and we can differentiate them separately because we have 3 separate terms in that bracket there. You might be happy differentiating these terms in this expression, but I'm going to make a slight detour here in this video just to go through the differentiation of each of these terms. We have 3 terms here, the first of which is a constant, and a constant, 5 in this case, the constant will just disappear when it's differentiated. This second term, a1 e to the power minus at, becomes minus a1 e to the minus at when differentiated. So remember that when we're differentiating an exponential term such as this, all we do is we multiply by whatever the coefficient of t is in that power. So in this case, the coefficient of t is minus a. It's being multiplied by minus a. And so all we're doing is we're multiplying that whole expression or that whole term by minus a. So that appears at the start. The last term, unfortunately, has to be differentiated using the product rule because it's a product of a2 times t times a to the power minus at. It's not just a exponential term in isolation. It's been multiplied by t, which is the dependent variable of the differentiation as well. So what we have to do in this case is use the product rule, which looks something like this. We've got dy by dt equals u dv by dt plus v du by dt. Hopefully you've come across the product rule before, but we're going to go through this particular term very quickly just to make sure that we're all happy. What we're going to do is we're going to break our term, which was a2t e to the minus at. We're going to break that into 2 terms and call them u and v. And so we're going to do it like this. We're going to say that u is a2t and v is e to the power minus at. So they're both expressions in terms of t, but they're not a product of 2 t terms. So we can differentiate both of these quite easily because du by dt is simply going to be a2. And dv by dt, just going back to that same rule that we mentioned before, all we do is we multiply by that coefficient. And so dv by dt is going to be minus a e to the minus at. And so by the product rule, sort of stitching all of these together, u dv by dt plus v du by dt, putting all of those in place, we have something that looks like this. And we can sort of multiply those brackets out a little bit and tidy up. But we end up with minus at a2 e to the minus at plus a2 e to the minus at. So taking all those points into account, our final differentiated expression looks like this because we differentiated 3 terms there, remember. 5 disappeared, the constant. The second term we differentiated to get minus a1 e to the minus at, and then the product rule gave us sort of two terms as a result of that rule. So we have this expression here is our final differentiated expression, minus a1 e to the minus at, and the result of our product rule, minus at a2 e to the minus at plus a2 e to the minus at. Now this is nasty. We only need this for just a moment to substitute those initial conditions, because hopefully we'll get a nice answer as a result. What we're going to say is, again, the initial conditions, not only is VC equal to 0 at time equals 0, we're going to assume also that the differential of VC, in other words dVC by dt, is also equal to 0 at time equals 0. So the left hand side here we're going to assume is 0, and all instances of t are also going to be equal to 0. So we'll have something like this. Again, we've got lots of e to the power zeros here, and all of those e to the power zeros are 1. Multiplying something by 1 doesn't change it. So we now have 0 equals minus a1 plus a2. This term, this last term, has disappeared because it's multiplied by 0, and that's going to make it 0. So we're just left with these first two terms here. And we also know the value of a, and we also know the value of a1. We've worked those two terms out already, so we can substitute those back in. Here we can say that now 0 equals minus 5,000 over 3, that was our value for little a, multiplied by minus 5, that was our value for a1, plus a2. If we multiply minus 5,000 over 3 by minus 5, we end up with 25,000 over 3. Again, a double negative when we're multiplying there, so that's a positive value now, plus a2. And so a2 is simply minus 25,000 over 3. So now we know the values of all the terms in our function, and so we can substitute these to find our result in the time domain. And so what we can say is, rather than this expression we had before, VC of t equals Vs plus a1 plus a2 t, all multiplied by e to the minus at. We know the value of Vs, a1, a2, little a. We can put all those in. We end up looking like this. And that's fine as our answer. There's nothing wrong with that. I'm going to tidy that up a little bit by, you'll notice that both terms inside the bracket are negative here, multiplied by the positive exponential term on the end. Better than that, what I'll do to just tidy that a little bit is I'll make the exponential term negative and the terms inside of the bracket positive. That's the same thing, it just, in my opinion, looks a little bit tidier. So now we have VC of t, that's the output voltage across the capacitor, is equal to 5, that was our supply voltage, Vs, minus e to the power minus 5,000 over 3t, brackets 5 plus 25,000 over 3t. Another reason I've made that little rearrangement there is because now it matches more closely the result that we found in the previous video using Laplace transforms. If you go back to that video again, you'll find that we got exactly the same result using Laplace transforms. So now hopefully you can see that these two results are sort of equivalent. Which one you prefer is up to you, but we are going to look at some more root finding methods for underdamped and overdamped examples. This was a critically damped example. We've seen this plot on our previous example when we used Laplace transforms, but here it is again. We see this sort of S-shaped curve, sort of increasing at first to this sort of transient shape, which then settles down into a steady state at around 5 milliseconds or 0.005 seconds. And that was a critically damped response there. We're going to compare, once we've looked at the underdamped and overdamped responses, we're going to compare the three responses. looking at that by itself, it's probably not obvious or significant what that means for it to be critically damped, but hopefully when we've looked at all three responses, we'll put them all side by side and you can see what makes that sort of critically damped response special compared to the other ones. But we'll leave this video here for now. I hope you found that useful. In the next video, we're going to do exactly the same thing, but we're going to look at an underdamped example of an RLC circuit.